So for this last module, we're going to put it together everything that we've learned so far in the course and do just a brief, what I would call your first coding example. And I think that the way that the things that it takes to become a good coder is to get enough of the basics and then move immediately in order to writing code that does something that you find useful. And as we mentioned in the initial part of the course so far, one of the main things that you're going to be expected to do in terms of your ability to code is to generate visualizations programmatically. And MATLAB has that function. So as we kind of see at the beginning of the slides here in Module 6, MATLAB can generate a ton of different plot types. But the most fundamental visualization that it can generate is what's known as a two-dimensional line plot. And that's where we basically take two vectors that are the same length, and we plot basically ordered pairs matching up the common elements of the two vectors with one on the x-axis and one on the y-axis. And that will make much more sense when you see it. But basically, we're used to plotting kind of in a math class point of view with continuous functions. But now we only have discrete functions. So we're going to pick the vector that's on the x-axis. We're going to go and get its first element. We'll go to that location in x. We'll find the matching value that we want to put on the y-axis, and we'll go up or down from there. Now, and if you think about why that's working, it's because MATLAB is a discrete programming language. So even when we want to generate kind of curves of kind of functional relationships that we generally think of as continuous, we're going to need to do that by relying on the fact that MATLAB, when it generates these plots, it interpolates. It actually takes the graphs, which are only defined at fixed points, and it draws a line between them. So let's actually just put this into action rather than talking anymore. Let's just see if we can do something useful. So what if we wanted to, and I know a lot of you are going down the ECE route, so sinusoids are going to be an incredibly important function you're going to know way too much about by the end of your coursework, especially after you get through the end of Fourier's theorem. So what if we wanted to, in MATLAB, kind of generate a visualization, sorry, closing my teams here, of a sinusoid that has a fixed frequency of 60 hertz and unit amplitude over 2 periods. I mean, this is just something someone might ask you to do. Write a script in order to show me what a sinusoid that has an amplitude of 1 and a frequency of 60 hertz looks like. And we know in our head what it looks like, but what if someone asks us to write code to do it? So let's actually go, and we know that naturally this is going to take a lot of different lines of code. So the first thing that I would do is I would generate a new script, kind of using the content I showed you in the first portion of the module this week. And then I would make a comment. I would say, this script plots a 60 hertz sinusoid of amplitude 1 over 2 periods. And even though you would never do this now, I would type in who the author is. And even though obviously files are timestamped, I would put in the date. And usually this is a date of last edit. And then usually when I'm writing code for my own development, kind of prior to releasing it to anyone else, I will put in what I'm given and what I know. So I know that I want the frequency to be 60 hertz and the amplitude to be 1. And you can always delete these comments later. Or if you're going to release a version publicly on GitHub, you might take these out, but keep them in your personal comments. We know that a sinusoid function has the form a times sine of 2 times pi times f times t, plus if we have a phase offset, which we don't in this case. So we kind of got to take what we know about math, take what we know about programming, and put the two together in order to generate this visualization. So how are we going to do it? Well, the first thing that we know is, and so I maybe add an additional thing, what we want, a plot of the sine function over 2 periods. So I kind of think of the way this is going to go. Well, I'm going to need to generate my plot. I need the values I want on the x-axis and the values I want on the y-axis. So in order to be able to generate that plot, which is the last thing I want to do, I have to define my x and define my y. Well, in this case, rather than call it x, I'm going to call it t, because these are values in time that I'm plotting. So the one thing I'm going to have to do is to generate my time values and generate my basically sinusoid values. How to do that? So what do we know about actually generating vectors in time? Well, in general, we know 2 ways to generate vectors that have a fixed start and stop point, right? We know the colon notation and we know the lens space notation. So in general, when you think about needing the time values, you're going to need the start and the end point. Well, the start point, usually when you think about mathematical functions, you just reference everything from t equals 0. However, we need to know what the end point is. And if you notice on the one side of things, we want to plot this function over 2 periods. And we were given that the frequency is 60 hertz. In addition, another thing that we know is that the period and the frequency are inversely related. So in terms of my actual code, I would start by defining what I'm given, that the fact that the frequency is 60 hertz, and then I would compute the period. Then I would go to generate the time values. Now I'm going to use a colon approach, and you'll see why I'm doing this in a second. I'm going to generate an array that starts at 0, goes to 2 periods. Well, if I have the period computed as variable t, I can compute 2 periods as 2 times t. Now, using this colon notation, the only thing that I need to do is to enter the inter-element spacing. Now, you might ask, well, first of all, why did I even put 2 times t in there? Why didn't I just get a number for t, 1 over 60, whatever that is as a decimal, and hard-code it in? Well, one of the key points of writing code is you want to make it general purpose. You don't want to write the same code over and over. And just like someone asked you to plot the graph of a 60 hertz unit amplitude sinusoid over 2 periods, next time they might ask you to plot it over 4 periods. And it's a lot easier just to change this number 2 to 4 than it is to change a hard-coded value. What about the spacing along that same lines? Well, you know that in order, remember, you're just generating discrete points. So ask yourself, if I'm just going to draw discrete values, if I'm just going to draw straight lines in between my discrete values, how many points per period do I need in order to generate a smooth plot? Well, say we didn't know that, but just kind of take me at faith. The way you want to do this is spacing a fraction of a period. So say I started by making this t divided by 2. And let's just see what happens. So this will give me all my t values probably. Now, the next thing I would do if I were you here is I would save my script and call it like test script. And notice that by default, this will save in your active working directory. And this is going to work quite similar if you're on the cloud version. That's okay. Just kind of follow with me and notice that things might be in a different place. That's okay. And I would just run my script. The key is to not run your script don't wait to run your script until the very end, or you'll have way too much things to debug. So you notice now I knew I wanted to plot down here, so I just put that kind of in place, but I haven't defined t and y yet, and that's all that's telling me. So I'm just going to keep that commented for now. I'm going to resave. I could left click on the save button, but get used to your keyboard shortcuts if you're going to be a good coder. So Control S, and then rerun it. You might say, well, Henry, why did you ever do that? Well, one of the reasons I might want to do it is just to do a little bit of a sanity check. I know if the frequency is 1 over 60, then the period is going to be like 16.7 milliseconds or 0.0167. So if I look at the values of time I generated, well, what do I know? It should end at 2 times that value. So 2 times 1 over 60. 0.333, that works. I know that I set my spacing to have the interspacing interval be a period over 2. So this is whatever the period is, 0, half a period, 1 period, 3/2 of a period, 2 periods. So I can kind of go through and make sure that I am seeing behavior in my code that I want. So I'm confident now that I'm generating a time vector that goes from 0 to 2 periods, and that each element is spaced by t over 2. Another way to say that is you're going to have 2 samples per period. Now think in your head of what a sinusoid looks like, and think if you just sample it at 2 samples per period, what you're going to get and where those points would be. And we'll see that in a minute. But how do we actually generate the sinusoid values now? Well, we want to create a new vector y, and we want to set it equal to. Now, the amplitude is 1. So we didn't code that in because when you multiply by 1, it doesn't change the value at all. But I'm going to actually put this in here. You might ask, well, why would you ever put it in here? Remember that when you write code, you want it to be general purpose for future use. The amplitude is 1 now, but it might not always be. In general, we could have a nice code here that plots any kind of sinusoid. So in general, the way that we know a sinusoid is given is you take the amplitude, A, which I've defined as a variable now, multiply by, we know that sine is a function, built-in function within MATLAB, sin. We're passing into the function which arguments. Well, you notice it actually it's telling you, hey, maybe you want to put t in there. But we know we want the parameterized form of the sinusoid, which is 2 times. But we're running into an issue here, right? Henry hasn't told us how you define pi. Maybe I need to type in 3.1415, whatever. But remember that another thing you should know about programming languages is anything that you think is done all the time has been done likely. And one of those would be actually specifying or hard coding in values of common constants like pi. So there's probably some keyword, some identifier that stores the value of pi. And fortunately, we're all on the same team. So the people that wrote this are also engineers like us. So they named it just pi. So and you can kind of see there was a little bit of a pop-up message there that shows you that when you type in pi, you're going to be able to access the stored value of pi. So what do we need? We need 2 times pi times f. Well, we have a variable corresponding to f. In our case, it's 60, but I won't write in 60. I'll write in the variable. That way this code is very robust. So 2 pi f times t. And we just did it. Question is, can we do that? Think about 2 times pi. That's a number. Times f. That's another number. Here we have a number times a vector. Can we multiply a number times a vector? Well, we could worry about it. We could stress about it. We could go to Google and see if we can do it. But the easiest thing as a programmer is just to try it. So save it and run it. Notice we got some values for y. Maybe you have the values of the sine function memorized in my head, but I don't. So naturally, rather than just generate those values for y, and notice that y is a 5-element vector, I should say, let me just be careful with that. How big was t? Yeah, t was 5 elements and y is 5 elements. So it's acting correctly, we think, but we won't know until we plot. So I'm going to uncomment the plot function, save it, and rerun it. You got a plot here. But it doesn't look good, right? Because what's happening is all these values are basically 0. Notice there's a little bit of variability, but we're multiplying by 10 to the minus 15th. That's basically 0. What's going on here? Think about your usual variation of a sine function. It goes from 0 to 1 to 0 to minus 1, and so on. Why might we only be seeing values of 0? Remember, we're spacing at every half a period, right? So what that means is that we're at most going to have 2 samples per period. If you think about sampling a sine function at half a period, what are all the values ideally? They're ideally 0. So what if you said, hey, I'm worried, I don't know what's going on, I'm stressed, I don't remember my math. What if you just look at this and say, hey, it's probably all looks right, but what if instead of 2 samples per period, we did 4 samples per period, meaning the spacing would be a quarter of a period? Let's just try that. Let's just rerun it. That looks more like a sine function. It's within the range that I would expect. But if you notice, it's way too, it's not smooth. It's way too much of straight lines. But remember, that's what MATLAB is doing. MATLAB is a discrete language. So you're sampling at the zeros, the maximums, the zeros, and the minimums. So what if instead of 4, I don't know, we did 8? Rerun it. You'll notice we're looking much more like a sinusoid. So since memory is relatively cheap, in this machine I have 16 gigabytes, I'm just going to do 100. I probably don't need 100 for my resolution, but that's okay. So sorry, I totally am having fat fingers this morning, so a little bit of editing to go back to where I wanted, from 0 to 2 periods with the inter-element spacing 1/100th of a period. And when you rerun that, you get the sinusoid that you wanted. So now you start to think about, well, what's all the different things that I could do? Well, that's a really weird unit here, right? These plotting in seconds for something that repeats 60 times a second is probably just not the right unit to use. As engineers, we just kind of look at this and say, hey, wouldn't it be nice if the decimal was just moved over 3 places? Well, that's just the equivalent of converting to milliseconds, right? So how do we convert value in seconds to milliseconds, right? I'm going to make you think about that a little bit for the homework. Another thing you might want to do is put some actual labels on the axes. How would we do that? Well, I don't know, but I probably would start by just looking at the help function of plot. These about labels. And remember, the key thing is you can read all of this documentation, and you can equivalently go to Google and search the same thing. Always start with example code. I'll give you a hint. The function to put on an X label is called X label. And you pass in a string. You actually define a string in MATLAB with these single quotation marks. Anything within them is interpreted as just a sentence that you want to put on, in this case, the X label of the graph. Notice if I regenerate that, eventually I'll have an X label on my graph. So we can start to make this into something that's more usable for telling a story. And that's going to be kind of in addition to some of the more basic elements of your homework assignment this week. That's going to be one of the ones that you get to dig into more detail on, because again, I want to make clear, I'm not trying to make you work too hard. It's just that in order to be a good software developer as an engineer, I'm never, unless we're going to just spend all our time together, which I'm sure from watching the videos, you don't want to do that. I'm not going to be able to teach you everything. So I'm going to kind of give you the basics. I'm going to give you some structured room to kind of do some exploration of some things that you need to be able to do if you are going to be expected to be an engineer that knows how to write code. And one of them is to be able to generate visualizations and kind of simulations of functions in discrete environments. So hopefully this was helpful to you, and I will get that homework up soon, and I will talk to you later.